So this is our chapter 2 test. It's not a review because we did the test, but going over the test solutions. That's the word I'm looking for. So let's begin. Number one, starting with the multiple choice part, says for the density curve shown, which statement is true? Density curve normal, density curve skewed right, skewed left, symmetric, or none of the above. Well, we can definitely cancel B and C out. And really the choice is between normal and symmetric, because it's definitely symmetric about that axis. So remember, the key to it not being normal is that normal is bell-shaped. So had this been normal, it would look more like this, where you would have some area outside here. So the correct answer for this is symmetric. Number two, for the density curve shown in question one, which statement is true? Mean is greater than the mean is less than the median and median are equal. The mean could be either greater or less, and then none of the above. Well, for anything that's symmetric, the mean and the median are both on that line of symmetry that I showed you. So the answer to number two is C. The mean and median are equal. Number three, suppose that a 16-ounce bag of chocolate chip cookies are produced with weights that follow a normal distribution with a mean weight of 16.1 ounces and standard deviation of 0.1 ounce. The percent of bags that will contain between 16 and 16.1 is about. So this question refers to the 68, 95, 99, 7 rule. And I told you I always like to sketch myself a picture. It helps me see it. So then I'm going to have my mean here, which they told me is 16.1. And then I'll go one standard deviation this way, one standard deviation that way. One standard deviation more that way, one more that way, and so forth and so on. If I were doing this on paper, I would fill in all the numbers. We're going to need that one because that's 16.0. So this rule tells us that between the two standard deviations, or one standard deviation on either side, you have 68% of the data, which means in each of these you would have 34%, because 68 divided by 2 is 34. And so that answer is C. 34. We're going to continue for number 4. For the distribution of cookie bags described in question 3, approximately what percent of the bags will likely be underweight? That is less than 16 ounces. So here's 16, so we're looking for the area and this part of it. So I have a couple of choices. I'm going to choose the easiest option. And the easiest option is not to put the percentages in each of those blocks and then add it together, but instead to recognize that from the median or mean over is exactly 50%. All this stuff I'm coloring green, 50%. Add to that the 34% that I did in number 3, and 50 plus 34 makes 84. So all that green that I just shaded in is 84%. And since the entire area under the curve is 100%, that means that the black region has to be 16%, which was B. All right, number 5. The plot shown at the right is a normal probability plot for a set of test scores. Which statement is true for these data? Now, A is not correct because we know that it should fit exactly on a line. All right, and this clearly does not. So A is out. Approximately normally distributed. Well, I don't think those dots are close enough to that line to even call it approximately. All right, so really we're down to C and D because we know there's a way to tell based on this. So when we look, we see that we have all these data points that are above in the lower values here, and that's what we talked about. That's going to mean that the data is skewed to the right. I guess I wanted that one. All right, let's see the next page. Which of the following statements are true? The area under a normal curve is always 1, regardless of mean and standard deviation. That is true. Let's give it a check. The mean is always equal to the median for any normal distribution. Well, any normal distribution is symmetric, and so that means that the mean and the median are the same. Let's give number 2 a check. The interquartile range for any normal curve extends from mu minus sigma to mu plus sigma. Well, we're going to have to investigate that one. If I sketch myself a curve, which I like to do, by definition, the interquartile range takes Q1, which will have 25% of the data, and Q3, which will have 25% on that part, which means between Q1 and Q3, you have 50% of your data. It's the middle 50%. But these values here, so I can make that go away. All right, these values, the mu minus sigma and the mu plus sigma, that is representative of 1 standard deviation from the mean. So if there's my mean, I go 1 sigma here, 1 sigma there. This is approximately 68%. So the IQR and these two values are not the same. So we're going to get 3 and X, and then go through and select the correct answer, which is 1 and 2. All right, number 7. The proportion of scores in the standard normal distribution that are greater than 1.25 is closest to. Always sketching my curve. I'm going to put my, it says the proportion of scores greater than 1.25. So this is going to be my Z here, and I'm looking for this area. So table A always gives me values to the left. So I am going to find that area using my calculator, which you can't see, that area is 0.8944. That would be represented, this part is here. But I want the black part, so I'll do 1 minus that. So let's see, that's going to be a 6, then a 5, then a 0, then a 1. And so that answer is A. All right, number 8 says, at right is a cumulative relative frequency graph for the 48 racers who finished the grueling 50-kilometer cross-country ski race at the 2010 Vancouver Olympics. Approximately what proportion of the racers finished the race in more than 2.15 hours? So we're going to have to do some reading on this. We're going to look for 2.15. It's here. And then we're going to go over. And that should have been straight, but we'll pretend it was. So this looks like approximately 0.55 to me, because there's 0.2, 0.4. I'm not quite to 0.6, so I'm going to guess 0.55. All right, but what that 0.55 represents is all of these people here, the ones that are less. We want these people, the ones that are more. So if this is 0.55, then this part must be 0.45. So we wanted C for that. Number 9 says, in the previous question, the mean finish time is that, and the standard deviation is that. The distribution is skewed right. What are the mean, standard deviation, and shape distribution of the z-scores of the same data? So the z-scores standardize it all, and it gives us a mean of 0 and a standard deviation of 1. So we're going to X all you guys out, because I know if I get the z-score that I'm standardizing it, and I'm making it mean 0, standard deviation 1. Now the choice is, what about the shape? Well, when you do the z-score, remember z equals, oh, don't move around like that. All right, x minus x bar over standard deviation. So that could be s or sigma, depending on what we're doing. What I'm doing is I'm subtracting something from it, and I'm dividing by it. All right, and we learned that to the distribution, if you multiply or divide, it doesn't alter the shape. It might change the values, but it doesn't change the shape. So this is going to stay skewed to the right. So the choice we wanted is D. Number 10, kitchen appliances don't last forever. The lifespan of all microwave ovens sold in the United States is approximately normally distributed with a mean of, let's get a pen back, 9 years and a standard deviation of 2.5. What percent is going to be more than 10? So this is kind of straightforward. We're going to do the z-score for it. So we want more than 10, so that's our x value. So 10 minus 9 over 2.5. A little calculator magic, that comes out to be 0.6 or 0.40. And so then that's the 65th, 0.45th percentile. Remember, I have my curve, and I want more than 10, so I want this stuff. What I looked up on the calculator was this stuff, but I had to subtract it. And so 1 minus that is 34.5%. Which was B. Yikes. Which was B. All right, let's look at the free response ones. Oh, so we start with some computer printout. And let's go over the computer printout really quickly in case there's something you don't understand. N means the number of people that are in the participating. So we have 30 for each. Then we have the mean, which is the average, the standard deviation, which gives us an idea about the spread. Minimum, Q1, median, Q3, and the maximum. That's our 5-number summary. So one car that Lamar is interested in is 4 years old and has been driven 40,000 miles. Another one is 3 years old and has 30,000 miles on it. How does the number of miles on these cars compare relative to other cars the same age? Provide appropriate statistical calculations to support your answer. So we're trying to compare two things from different distributions, so standardizing them is always a good way to go. So we're going to count or calculate the z-scores for both of those. So I'm going to do z sub 4 to stand for the 4-year-old car, and that's going to be 40 minus 56.68, which is the mean for those, over 17.82, which is the standard deviation, comes out to negative 0.94. Then I'm going to do the z-score for the 3-year-old, so 30 minus 33.33 over 12.70. gives me negative 0.26. So now we have to think about it logically, kind of. We have this normal distribution, and here is the average number of miles driven by either car, because we've normalized it so we can compare them. The 3-year-old car is at negative 0.26 standard deviations, which is about right here. So it's less miles than the mean is for other 3-year-old cars. But when you look at the 4-year-old cars, they're almost a whole standard deviation away, which means significantly less miles compared to the rest of their distribution. So this does much better compared to its fellow classmates. I guess we can use that word. They're in the 4-year-old class. Alright, number 12. Based on the information above, estimate the number of 4-year-old cars Lamar looked at that have been driven more than 42,000 miles. So when grading your papers, this got some of us, this part right here, where it says estimate the number of 4-year-old cars. A lot of people gave us the percentage, but they didn't estimate the number of cars. So let's see how we do that. We want to calculate the z-score first. So, oops, got to write. So z is equal to 42 minus 56.68 over 17.82, which comes out to negative 0.82. All right, and negative 0.82 corresponds to 20.61. It's 0.2061 on the table, so as a percentage, that's 20.61%. But remember, we're looking at more than. So what I just looked up was, here's my z-score at negative 0.82. I just got that stuff. That's not the stuff I want. I want this stuff. So if that is 0.2061, then this is 9397, or 79.39%. Getting here was good for half credit, but we had to go all the way to the estimate the number of 4-year-old cars. So I'm going to apply that to the number of cars that Lamar drove and multiply that times 30. So I can do this out, but it's going to come out to be approximately 24 cars. I think it was 23.81. I wrote on somebody's paper, have you ever driven 0.81 of a car? Make sure your answers make sense. There's no such thing as 0.81 of a car, 0.81 of a person. Round up appropriately when it makes sense. Alright, number 13 says to estimate the 60th percentile for mileage on the cars Lamar found that were 4 years old. So we're still dealing with the 4-year-olds. There's my curve. The 60th percentile means I'm going to have 0.6 in here. And so you can't see it, but right now I'm doing the inverse norm of 0.6, and I get a z-score of 0.25. So then I'm going to use 0.25 is equal to x minus the mean divided by the standard deviation. And then I'm going to do a little bit of algebra, cross multiply, and then add the 56.68, and that comes out to be about 61.1. Now, you don't want to get dinged when you take your exam in the spring, so just doing 61.1 isn't good enough. What we have to remember, and they're very picky about this, and I want you guys to do really well, is that all values are in thousands of miles. So when I come back down here, I want to interpret this in context. And so I'm going to say 61 1,100 miles. All right, let's go to the last page. A researcher wishes to calculate the average height of patients suffering from a particular disease. From patient records, the mean was computed to be 156 with a standard deviation of 5 centimeters. Further investigation reveals the scale was misaligned and that all readings are 2 centimeters too large. For example, a patient whose height is really 180 was measured at 182. Further, the researcher would like to work with statistics based on 1 meter equals 100 centimeters. What would be the revised values for the mean and the standard deviations of the patient's height? So if you subtract 2 from every single value, then that's going to affect the mean by exactly that. So I would do 156 minus 2 would be 154 centimeters. But he wants to work in meters. So then I'm going to divide the 154 by 100 to put it into meters. And so I'm going to get a new mean of 1.54 meters. There we go. Now, standard deviation will not be affected by the subtraction. All right. So the standard deviation would still be 182 centimeters as far as the subtraction goes. However, it does get affected by the division. Sorry, I was looking at, where did I get the 182 from? Yikes. If I could erase that part, I would, but I can't, so I won't. But the standard deviation was only 5 centimeters, not 182. So let me do that. Alright, so what I said was right, that the standard deviation won't be affected by that subtraction. But it will be affected by the division. So we'll do 5 divided by 100, and I get 0.05 meters to be my new standard deviation. I still don't know where I got. Oh, there's 182, but yikes, now I'm throwing stuff around. All right, there's where I got the 182. Like I said, I would erase, but I can't. All right, let's go. During the 2009-2010 basketball season, the number of points scored in each game by the Boston Celtics was approximately normally distributed. Would that mean... Oh, that's not the one I want. And that's standard deviation. What is the 33rd percentile of points scored by the Celtics? So the first thing we want to do is, here's my picture. Well, my picture's not very good. That's better. So the 33rd percentile is this stuff. So I need the z-score associated with that. So I'll do the inverse norm. And I'm going to get, it is negative 0.44. And that's my value and my mean and my standard deviation. And a little algebra 1 magic comes out to be 94.58, which I'm going to approximate to 95 points per game. You want to make sure that you're always interpreting in context. I remember somebody I think said 95% here maybe. We definitely don't want to do that. Make sure you're keeping your units right. So this is 95 points per game. The mean number of points scored by Los Angeles Lakers was 101.7, and what proportion of their games did the Celtics score more than the Lakers' mean score? So now we're looking for more than 101.7. So that's there. So let's calculate our z-score. Z is going to be 101.7 minus the 99.2 divided by the 12.5. And that comes out to be 0.24. I'm going to look it up on my table, and the table is giving me this stuff with a value of 0.5948, but I want the blue shaded in, so I'll do 1 minus the 0.5948, and that's going to be 2504. Or 40.52%. But it said proportion, so I didn't need to change it to percent. Okay, this is the one that I said would be fun. Mr. Wilder has a reputation for holding his classes a few minutes after the bell has rung at the end of the period. In fact, it seems he ends class according to his own internal clock. Below is a density curve that describes the distributions of times when Mr. Wilder ends his class. Negative values mean before the bell rings, positives are after. What proportion of time does Mr. Wilder end class within 1 minute when the bell went off? Shade the area on the graph and show how you found the answer. So this one I told you was more kind of a logic problem, and it was. And I actually took two answers for this, depending on how you explained it. Now, one answer is that here's the bell. So I've got 1 minute after the bell and 1 minute before the bell. All of this stuff, I say stuff, all the blue shaded region represents area within 1 minute of the bell. And that's what it said, within 1 minute of the bell ringing. So I have 1, 2. If I imagine this is 2 and 3, and those are all minutes, then I can see that I have 5 equal sections. So 2 of the 5 are shaded, which is 0.4 or 40%. But when I reread it a second time, I could see a valid interpretation of being after the bell rang. So I can't count this because the bell hasn't rung, and then within 1 minute would be that part. So that would be 1 over 5, which is 0.2. So I took it as long as you showed me that graph. I don't want to pick on anybody, but somebody showed me this graph without the blue stuff, and that didn't count because it did say after the bell, and so that would have been a valid block there. All right, that was our test. We did much better on this. It was our highest average of the year, and that was with one remarkably low score thrown in there. So good job.